So now I'm very pleased to introduce our invited speaker for Crypto 2024, Karthik Bhargavan. Karthik's research focuses on the intersection between formal verification and cryptography, with the goal of developing new program verification techniques that enable formal analysis of real-world security applications. Karthik has been involved in the design, analysis, and standardization of IETF standards on TLS 1.3, hybrid public key encryption, and messaging layer security. He was part of the Project Everest and me-TLS teams that built a formally verified implementation of TLS 1.3, which won the inaugural Levchin Prize for Real-World Cryptography at RWC 2016. In addition to his role as a researcher at INRIA, he is co-founder and chief research scientist at Crispin, a startup building and applying formal verification tools for real-world security systems. Today, Karthik will discuss his experience in integrating formal verification in cryptographic standards and applications. Please join me in welcoming Karthik to the stage.
Thank you, and thanks for the kind introduction. So yes, today I'm going to be speaking about some work that many colleagues and I have been doing for about a decade now. I hope it'll be useful to you. So when my colleagues and I in my field are looking at cryptography, we're really thinking about three kinds of artifacts. So out here at Crypto, we look at high-level designs, right? So functionalities, crypto constructions, protocols that achieve some super cool new security goal or address a new threat model. We write down mathematical descriptions for them, and to evaluate this, we write paper proofs, and we have peer review. And the kinds of things you might want to ask is, well, is the math correct? Is the proof correct? So this is one of the concerns that you might have. Conversely, if you want to actually deploy this crypto, it probably needs to be integrated into some protocol or some standard. And there, the artifacts are completely different. There are standards and specifications, which are detailed technical descriptions of the protocol, which have to flesh out all the computations, all the encodings, all the validations, a lot of boring stuff, so to speak. And there, not only that, the document that you produce has to be ready for community review, reviewable by a much larger community than just the cryptographers. These are engineers, these are network designers, these are protocol experts who have to be able to understand your security argument, your proof. And that's a much higher bar. And they're asking questions like, well, is this standard ambiguous? Is it implementable? Is it secure in the real world, for example? And of course, finally, the thing that most people care about are the deployed implementation, because that's what they get to use. And implementers, they're concerned about completely different things, like efficiency, optimizations, APIs, state machines, key storage, these kinds of things. And they test their code, they audit their code, they fuzz their code because they're worried about, is my code buggy? Does it have side channels? Okay. So three different kinds of artifacts, three different kinds of questions. But the interesting thing is there are formal methods which are available for all three of these kinds of problems to answer these kinds of questions. And not only that, I would like to emphasize that none of these artifacts is static. They keep evolving over time. Implementations inform new designs, which inform new versions of the standard and so on. So formal methods can not only answer some of these questions, they're one more tool that you can use to answer these questions, but they can also help you keep answering these questions as these artifacts evolve. So what I'm calling formal methods for cryptography is also called by the name computer-aided cryptography or high-assurance cryptography. And it generally refers to the idea that you want to be applying formal machine-checkable approaches to the design, analysis, and implementation of crypto. And all of the ideas I'll be discussing today are in that systematization of knowledge paper that I'm citing there with several colleagues. The key word there is machine-checkable, which means tools. Tools for analyzing your designs early so that you can find attacks or uncover assumptions that you may not have realized that you were making. Tools for comprehensively analyzing the specification or standard before it gets published. Tools for analyzing your code to find bugs or side channels. And tools that can help you do this over and over again as these artifacts evolve. This is a very active area of research. Some of the older ones among you may have already been there when Gilles talked about computer-aided cryptography at Eurocrypt 2017 or last year when Peter was speaking about high-assurance crypto at CHES. And there's also many recent papers on this topic. Even at Crypto 2024, there's a paper on Kyber, which uses machine check proofs. But beyond the crypto conference world, there is an entire conference called IEEE CSF, and many other papers get published in Oakland, CCS, and so on around this topic. So my own work is more on the bottom side of this triangle. So I have been concerned more about protocol standards and specifications and asking questions like, is this protocol secure when I consider all of its gory low-level details? Or looking at implementations of crypto algorithms and protocols and asking, is there an attack on this? Can I prove that this is correct or secure? So many of the examples I'll be taking will be from this side of things, although I hope that many of the techniques I'll be describing will also be applicable to your own work. If there is one message I want you to take away before you fall asleep in this afternoon session, it is that, one, there is a wide range of formal methods for cryptography, not just one, okay? And using any of them, depending on your application, could actually speed the deployment of your cryptography and definitely clarify its security in real-world scenarios. So if any of you have seen previous papers or talks on formal methods, you might feel like, oh, isn't this about like these massive sort of heroic efforts involving dozens of researchers for 5 years? Sometimes, yes, but it doesn't always have to be that way. In fact, I'll show you an example where you can have a big impact with fairly modest effort. And my last goal here is to encourage many of you to just pick up a formal tool and try to use it. It could be Sage, it could be Lean, it could be F-star, it could be Proverif, Cryptographic, whatever. Because the more you use it and the more you demand of the tool developers, I think these tools have a chance of becoming more effective for your use case. But if you don't use them, they'll just stay in their current state and move slowly in directions that may not be of benefit to you. So to start with, let's look at a big success story for formal methods in crypto. And yes, it is one of those large heroic efforts involving dozens of researchers in many, many years, but we'll try to get some lessons out of this. So between 2014 and 2018, the Internet Engineering Task Force decided to standardize a new protocol called TLS 1.3. It is a complete revamp of the protocol. They do this every decade or 2 decades or so, which improved both the performance of the protocol, but also aimed to improve its security. So far, it was pretty normal. But what was unusual about this effort is from the very beginning of the standardization effort, they decided to involve cryptographic researchers in the design and the analysis of this protocol, so that the goal was that before the protocol is even published, we should have many proofs of security for it. So we are really sure about it this time. And this succeeded. Many groups got involved. There were many pen and paper proofs published in many different conferences, and several machine check proofs were also published using various tools, which I will talk about. So if you look at where the protocol was in 2014 and where it ended up in 2018, and if you tried to explain it to somebody and drew it on a whiteboard, you might actually draw the protocol like something on the right, because you don't have time to do all the details. So you say, well, yeah, it's basically unilaterally authenticated Diffie-Hellman. It has a signature and a MAC in some particular sigma-like construction, but sigma is Hugo-Krochek sigma, not the other one. And so this is what it looks like. And you could have written that protocol down in the 1990s and nobody would have been surprised. So you look at that and you say, well, what took you 4 years, right? And what took us 4 years is that we actually looked into all the details. With every draft of the protocol was proposed, the protocol designers and the researchers talked to each other, that they explained what they were doing to each other, so that then one group would go take off a draft, do a proof about it, come back, say, oh, there's a problem. Can you please fix it in the next draft? It'd get fixed. And another group would take that new draft off and do a proof. So there were proofs at various stages, as you can see, of this standardization effort. The places which drafts which are marked in red were ones in which the analysis found attacks. The ones which the papers marked in green are those that use machine check proofs. So you can see the trend. As the protocol got closer and closer to standardization, as it was fully fleshed out, there were more and more machine check proofs that could encompass the whole standard. And so this is considered a success story. We actually ended up with lots and lots of analyses. And not only that, it had a big impact on how protocols are designed today. At the IETF, in working groups like MLS, Lake, and TLS, if you're proposing a new protocol, the working group chairs often ask, do you have a formal proof? Even if a pen and paper proof, you have to give it to them. A machine check proof, even better. Even industrial protocols, some of you may have followed Apple's iMessage, which had this new update called PQ3. And when they published the spec or the blog post about it, they published it with 2 formal analyses, one of which was machine check. I'm going to talk a little bit about how Signal and PQXDH protocol is also analyzed with formal methods. So it's had a big impact, but what lessons can we take from it? Well, clearly, TLS-13 is a once in a decade, once in a generation kind of project. We're never going to get that many groups focused on analyzing one protocol for 4 years. That's just too much work. But still, we can learn some lessons. The first thing was during the development, the interactions between designers and researchers was actually crucial because there were many places where the researchers did not understand why they had to model this particular feature, and the designers had to explain their constraints to them. And that enabled us to kind of get motivated in analyzing bits of the protocol we would not have analyzed otherwise. Contrarily, the researchers could come back and say, hey, you know what? If you write the protocol in this way, it's much easier to prove. Do this key separation here, that makes the proofs much easier. And the protocol designers were well up for changing the protocol to make the proofs easier. So this interaction was very useful in both directions. The second lesson was that low-level details matter a lot because the protocol is actually the thing on the right, not the thing I showed you on the previous slide. And each of those details actually hides attacks. And many of the attacks were found in low-level details. The third point is that even if you have a really long protocol with 20 sequential messages, it's actually not very complex. You can actually think about it as you can collapse many of these messages together. You can actually analyze it very easily. What makes the complexity really blow up is when you have many different modes, compositions. You have different key exchange mode, different authentication modes that you have to compose together. That really gets much harder. And the last point, which I wasn't very aware of when I started that process, is that communication is key. So when you can't just come to the working group, give them proof and go away. They'll say, wait, hang on, explain to us. What are you proving? Why is this proof correct? You have to be able to explain to a non-expert, what is this proof that you have produced and why it's actually the right property to prove? And not just that, they will immediately come back to you with more questions. Well, what if I add this feature? Does the proof still work? Can you also prove this additional property? And you can't say, hang on, I'll go back to my desk and 3 months later come back with a new proof. No, you have to be able to give answers very quickly. And in all of these respects, formal methods have a little bit of an edge over pen and paper proofs. They're a bit more work, but you can deal with them, these kinds of questions much easier. As an example, after TLS-13 was standardized, people realized, hey, we encrypted most of the handshake, but we forgot this one thing, and the client hello is not encrypted. It contains the server's name in the clear, which means that although we wanted some privacy guarantees for TLS, in fact, a lot of privacy guarantees we're just leaving on the table. So they decided to work on a new extension called the encrypted client hello. It's still not standardized. It's still a draft, 20 versions in. And they tried to fix this. But the first few designs for the encrypted client hello were actually broken. An active network adversary could actually distinguish between which server you're trying to connect with. So the question came up, hey, we all have all these proofs of TLS-13. Couldn't we use them to try to prove that the encrypted client hello actually works? More importantly, can we prove that it doesn't break all the guarantees we've already proved so far? So what we did for this is, in fact, we used one of those machine check proofs that we had already done. We took the probative proof of TLS, extended with the encrypted client hello, proved that it doesn't break any of the properties we had already proved. And this is actually an important one. We don't want to break the previous properties. And then we did the work of adding privacy goals, trying to prove the privacy properties, which was its own research project, resulted in a paper and so on. And that was a bit of work because that's a new property you're proving. But at least we had something to start off from. And I cannot imagine that we would have been able to do the same thing with the pen and paper proof if we were the people who had written that pen and paper proof, maybe. But it's clear that here having a machine check proof was an advantage. Okay, so that was the TLS-13 experience. We had lots of lessons, but of course, we're never going to have those 4 years to analyze protocols again. What can we do on a shorter time frame? Let's look at Signal's PQ XDH. So all of us here use Signal. Many of us probably know the ins and outs of it completely. But still, if you don't know about Signal, well, when you start a Signal conversation with somebody, the first protocol that kicks in is called X3DH, which establishes initial keys between you and your correspondent. And then as your conversation proceeds, a different protocol called double ratchet kicks in, which keeps updating the keys. And together, these two protocols aim to provide mutual authentication, post-compromise security, forward secrecy, and a certain form of deniability. Here, we are mainly concerned with the first part, X3DH. So in September last year, Signal decided that, well, they were afraid that the conversations that Signal participants were having today will one day when a quantum adversary comes in be decryptable. So how do we prevent this? So they decided to add a little post-quantumness into X3DH and call it PQXDH. So the top left here is classic X3DH. There's actually 4 Diffie-Hellmans happening there. Yeah, 4 Diffie-Hellmans happening there. And all of those 4 Diffie-Hellmans are going to be concatenated and KDF'd into the key that is going to start off the session. So their idea was, hey, let's also do a post-quantum chem. And they chose Kyber 1024, Kyber round 3, 1024 for this. And we'll encapsulate a shared secret SS. And we will mix the SS alongside the 4 Diffie-Hellmans together. And that'll be our initial key. A fairly straightforward idea. More interestingly, it doesn't have to change any of the infrastructure. We are already downloading all these signed Diffie-Hellman keys from the server. We can also download a signed post-quantum public key. So it exactly fits into the flow. In the message that we are sending across from the initiator to the responder, there's one extra thing we have to send, which is the chem ciphertext, which we didn't have to send before. But other than that, it just fits very nicely into the protocol. So if you think about this as a protection against harvest now, decrypt later adversaries, this is kind of the minimal change you can do to X3DH and still get that, try to get that property. But X3DH is very well understood. There are many proofs for it, pen and paper proofs, machine check proofs that are comprehensively analyzed in many, many different models because it's a very simple protocol. So we have all those guarantees for X3DH. Can we do the same for PQXDH? Is it as secure as X3DH in the classical model? And does it actually achieve post-quantum security in this HNDL quantum model? So when Signal published this, we decided, okay, let's try to do a machine check proof because we have analyzed X3DH before. How hard could this be? So the first step in all of these formal verification projects is to take your technical description, which is on top, and to write down a formal specification for it. What does it mean? All the protocol actions, all the messages, all the cryptographic assumptions, the security goals, and the threat model, what keys can get compromised by who, when, and so on. So you have to note down all of those things, and that's when you have your formal specification of this protocol. And then what we decided to do, that we would analyze it using 2 tools. The first is called ProVerif, which can find attacks against those security goals. It searches for attacks automatically. And if it finds an attack, it might mean that our model was incorrect or that the protocol was actually buggy. So depending on that, you might fix the model and rerun until you find no attacks, at which point ProVerif produces for you a theorem that none of the attacks you programmed in your model actually are in the protocol. And once you get there, you might say, hey, let's do a crypto proof. So the second tool we use is called Cryptographic, where we take the same model, we pass it through this tool called Cryptographic, which tries to build a cryptographic proof that the protocol is secure. And if the proof fails, it might be because one of our assumptions is not strong enough, in which case we refine the assumptions, or it might be that the protocol is broken, in which case we have to fix the protocol. But if we go around the circle a few times, we should be able to get to a proof. So that's what we did. So what does this look like for PQXDH? So PQXDH is an extremely simple protocol, one message protocol between 2 roles. So the scenario we set up is that there is an unbounded number of endpoints, and any endpoint could be an initiator or it could be a responder. The identity keys of all of these endpoints have already been distributed out of band beforehand. So let's forget about the identity keys, but all other keys are actually downloaded from the untrusted network. The specification of the initiator is what you see on the right. It's written in this language called the applied pi calculus, which is supported by both ProVerif and by Cryptoverif. The exact syntax is not important. What's interesting here is that you're forced to specify all the cryptographic operations, obviously, but also what exactly gets signed, what exactly gets encrypted, what goes in the KDF, what are the exact encodings that you're going to use, what goes on the network and when, and so on. So you have to make it very precise. And I will say that writing down this kind of a machine checkable specification often already shakes out a bunch of things, especially ambiguities. While writing down the spec, we could already start noting down saying, oh, the signal spec doesn't say this about AEAD, I don't know what they're doing, and so on. And so the first set of questions goes out to Signal immediately after writing the spec, saying, hey, how exactly do you implement this? What do you mean here, and so on? Because when you write down the spec, you have to make these things precise. Once you've written down the spec, we can start analyzing it. The first analysis we're going to use is ProVerif, which is a symbolic analysis, which is in a cryptographic model called the symbolic or $YAO model. And the idea is that the crypto primitives are treated algebraically. You write down the functions that you're going to use and write equations describing the relationship. So on the right-hand side is a naive or simplest possible model of chem encapsulation and decapsulation. We can try to make more refined over time because this is a programmable model. You can actually program your assumptions in there. So once you define your crypto assumptions, then you set up your scenario. In the bottom right, we have set up the scenario saying, we're going to have an unbounded number of initiators talking to an unbounded number of responders. So there's any number of sessions between the initiators and responders, and any subset of them can get compromised. Okay, we give the attacker the power to compromise any subset of them. So what's interesting about Proverif is that, and tools like this, like Tamarin, is that they allow you to program a threat model in there. So you can have a class of attacks and then expand the class of attack and say, oh, you know what? I wonder if the key validation here is important. So let me add invalid keys to the model and see what happens. Let me add reuse nonces to the model and see what happens. So you can keep adding and extending the attacker model to see what attacks come out from the protocol. So once you've written down your attacker model, you write your security goals. You can write authentication, secrecy goals, indistinguishability, privacy goals as well. And you can press the button and Proverif will hunt for an attack. Okay? If it finds an attack, it'll produce a trace. It'll say the attacker does this, then sends this, receives this, does this, boom, he breaks the security property that you had. But if there was no attack, then it says, okay, I searched through this entire class of attack that you programmed into your model, and I couldn't find any attack. And that's a symbolic security theorem. But in some cases, it might run out of memory and not terminate. It does that very rarely because this is fundamentally an undecidable problem. There are nice papers about what it tries to do and why that's undecidable. But in most cases, you get in the first two categories. What about Cryptographic? What is that good for? Well, however precise I get my assumptions and how much ever power I give to the attacker in the symbolic model, it doesn't correspond exactly to the classic standard crypto assumptions we are used to out here, right? So Cryptographic allows you to actually do a classic game-based proof using standard assumptions like INCCA, CAMs, UFCMA signatures, the standard things. You can also code in your new assumptions yourself using probabilistic equivalences. There's a whole language for that. But for most of the standard assumptions, it's already in the library. So you can just use them. The syntax of the processes and the goals and the queries remains the same, but the proof is completely different. It's not a push button tool. Instead, what you're doing is constructing a cryptographic proof, which looks like something on the right. It says, apply this game, do the simplification, apply this other game, do this other simplification, and so on. It's a script for developing a full crypto proof. So it requires manual guidance from the user. Not so much, but still, it requires manual guidance. And all the transformations are machine checked. Of course, if your proof fails, it means that maybe there is an attack, but it's not going to give you a trace. It's not like Proverif. It's just going to say the proof does not work. So you have to interpret it. On the other hand, if the proof works, it's going to give you a concrete formula about the attacker's advantage. This may not be the most precise formula you could state for the protocol, but it's still quite close and quite useful as a bound on what the attacker's advantage is. So that's Cryptographic, that's Proverif. What about quantum? Now, how do you model the quantum adversary? In the symbolic model, modeling the quantum adversary is very easy because we just give the attacker more and more power. So we say, okay, we have an event called the quantum apocalypse, after which the attacker can break all the discrete logs he wants to. Okay, so this is the power you can give to the adversary. And then say, press a button and ask Proverif to search for attacks that rely on breaking classical primitives without breaking symmetric encryption, without breaking post-quantum caps. And Proverif will search for these kinds of attacks. When you're trying to do the proof, though, that's a different deal. You have to figure out what your model is. Luckily, there was a recent extension of Cryptographic, which is what we use, which basically shows how to do computational crypto proofs in Cryptographic, which are sound against what they call a passive quantum attacker, which you think really as the harvest now, decrypt later attacker. That is, the attacker can break Diffie-Hellman, but only after the session has been completed. So we use that to do our proofs. Okay, so now we have the setup. What do we find about this protocol? The first thing we can find using symbolic analysis, for example, is this key confusion attack. So like I said to you, we have added this new key to X3DH, which is the post-quantum public key. So the initiator is going to download the signed Diffie-Hellman key, the signed post-quantum key, and then start doing its computation. And what if the attacker swapped the two? Swapped the post-quantum public key with the Diffie-Hellman key. Okay, in reality, the Diffie-Hellman key is the 32-byte X25519 key, and the post-quantum key is the 1500-byte Kyber 1024 key. So it should be very difficult to swap the two and not notice a difference. But let's assume that the software is so silly that it just fills it out with zeros or something, but it kind of allows you to swap the two. Now you're going to be doing a post-quantum chem with an X25519 key, obviously completely broken. You don't have any post-quantum security, okay? And that can only happen if your encodings of those two keys can collide, of course. And if in your model, you're not validating any of the keys, you're just taking the key and then encrypting to it, which of course can happen too. But this actually uncovers those assumptions. The fix is very simple. You just add context everywhere, right? So you just make sure that all the keys are disjoint, all the signatures have some labels in them to make sure that you cannot confuse these things together. But this is actually a representative of a much more general class of attacks, which we have to be careful about these days when we are adding post-quantum things into existing protocols. Because you might think, oh, I'm just making it more secure, but adding this new feature may actually have bad interactions with what was in the protocol already and cause attacks not only in the new feature, but also in the old protocol. Because the other attack that is happening there is that in X3DH, suppose I'm just doing the normal X3DH, I don't want to do post-quantum nothing. You could give me a Kyber key. I might take the first 32 bytes of that Kyber key and try to do Diffie-Hellman with it. And now suddenly my guarantees from X3DH are weaker because Signal decides to support PQXDH. So these are things we have to be particularly careful about. So suppose we fix that, and Signal, of course, was doing the right thing in the implementation. It's just that this protocol spec did not specify it. So suppose you fix that, are we done? No, there's another interesting but kind of technical vulnerability, which is a chem re-encapsulation vulnerability that comes up. So bear with me. So the issue here is that the attacker has somehow compromised an old post-quantum secret key belonging to the responder Bob. The responder has deleted this key, has moved on to a whole new set of keys, and will never use that key again. So what the attacker can do is send to the initiator this old post-quantum public key and say, okay, here's Bob's post-quantum public key. The initiator encapsulate an SS, a shared secret, for this old compromised key. You take that, you decapsulate it, and you re-encapsulate, as an attacker, the same shared secret to the responder. So from the responder's viewpoint, it looks like a perfectly formed message. It completes the protocol. The initiator completes the protocol, but in fact, their transcripts do not match. The initiator thinks it's talking to post-quantum key old, whereas the responder thinks it's talking with post-quantum key new. Okay, so this breaks an integrity property and also breaks a certain kind of session independence property. And the session independence property is that if you manage to break one post-quantum private key belonging to the responder, you can now break the security of all future connections, even if they appear to be with new post-quantum public keys. The fix is, again, very easy. You just mix in the public key of the responder either into the shared secret or into the AED or something. But the eagle-eyed among you would have noticed that, hey, but Kyber already does that. In fact, in the Kyber NCCA Chem construction, you already mix the post-quantum public key of the recipient into the shared secret. So that attack is actually not possible with Kyber. It's true. But when we are doing the proof, we don't know it's Kyber. All we know is that it's an NCCA Chem, and NCCA does not prevent that Chem re-encapsulation attack. So in order to prove that PQXDH with Kyber is secure, we needed to formulate a new property. We call it semi-honest collision resistance, but whatever, you can call it whatever you want. And we proved that Kyber round 3 is SHCR, and SHCR plus NCCA is enough to guarantee the security of PQXDH. What's interesting here is, I think, to my knowledge, this is the first real-world example of one of these chem re-encapsulation vulnerabilities due to post-quantum chems, and it is a practical example to contribute to the current discussion around chem bindings and so on. All right, so we did all those analysis, we fixed all those things, we had lots of conversations with the Signal developers, they accepted our recommendations, they proposed some changes, we did the proofs for those changes, and then a new version of Signal came out, PQXDH came out 1 month later from the first one. So this whole process of analyzing the protocol, finding attacks, talking to them, fixing it, doing the proofs, new version with proofs was 1 month, which is a much bigger improvement over the 4 years of TLS. So what lessons can we take from this experience, this much more contracted experience? The specification was very useful because it's a mean of communication between the designers and the researchers. Before the specification, we are always worrying about English text, but the first time we wrote the specification, it started really making the conversations more meaningful. And it already shook out some ambiguities. The symbolic analysis was useful for finding some attacks, yes, but more commonly, it was useful for reconstructing attacks. Like you look at the protocol, you say, I think it might be vulnerable if this particular keys or these keys were compromised. So you add a whole bunch of key compromise into the system and see what ProVerif finds, and ProVerif will usually find the attack or say, no, this prevented because there was this other thing that you forgot about. Then the machine check game-based proof that we did here was fairly easy. Of course, it also shook out the SCEM re-encapsulation assumption that we needed. And it was able to handle passive quantum adversaries without any problem. That's a new development, but these tools are getting good enough to do this. On the other hand, PQXT8 is the easy case. The really small protocol, 2 parties, 1 message, up to 10 crypto assumptions. The assumptions themselves are pretty classic. And we are really analyzing the high-level design. If we started going into the double ratchet, like the PQ3 guys said, or state management of groups, or anonymous credentials like Signal also supports in some places, or try to prove that lib Signal implementation is secure, all of those things would have been much more challenging. So this is actually the happy case of formal verification. Okay, so I'll talk a little bit about what are the unhappy cases and how far we can go. So let's look at a third example, which is MLS, the messaging layer security. So after TLS, the IETF decided, okay, let's do a new protocol, and this time we'll try to secure messaging, secure group messaging, in fact. We want to be able to support groups with up to tens of thousands of members, but we want the same guarantees as Signal. We want forward secrecy, post-compromise security. But since we have to handle such large groups, we have to be able to do group operations like adding people, removing people, updating people very efficient. Okay, so it's a completely new construction this year. And they re-engaged the researchers, some of whom had been working already on TLS, and said, can you help us with the design and analysis of this? And in fact, the first few designs of this protocol came from the research side, not from the designer side, because in fact, this was so new that in fact, even the designs were researched. The first design that came out was called asynchronous ratcheting trees. And soon after that, I and my colleagues proposed this protocol called TreeChem. And both of them are very similar, at least at this level of abstraction. The basic idea is you arrange your entire group as a tree where all the members are at the leaves. Each member has a private public key pair, but also there's a private public key pair associated with each subtree. And the invariant you maintain is that the private key for a subtree is known only to the members who are underneath that subtree. And if you can maintain this invariant in the protocol, then in fact, you can do group operations like adding people, removing people, updating people quite efficiently. Typically with order log n public key operations, rather than order n public key operations, which was what was standard with Signal and WhatsApp and sender keys and so on. So this could be a logarithmic scale protocol. Of course, once it gets into the standard and starts evolving, a lot of details come in there. So we designed this protocol. We are very happy. It's very elegant, we thought. Also, they said, we have all this experience verifying this protocol. Let's use machine check proofs to verify TreeChem. And we hit a wall. Because although there are many pen and paper proofs of this, this is a particularly challenging example for formal methods. And what's challenging here? The first thing is that this is a recursive data structure, right? It's a tree with 10,000 members. So it pretty much might be infinite from the viewpoint of the tool. So which means that almost all the proofs have to be by induction, and the support for induction in automated tools and symbolic analysis, and also in computational tools like Cryptographic was very limited. So it's already hard, but solvable. What makes it particularly hard is that this tree is dynamic. It's not a static tree, which means there could be people who leave, like you see the third member at index 2 has left the group, and somebody could be added later on. So there could be lots of gaps and holes in the tree, which means that the actual protocol actions taken by any member of this group depends on the structure of the tree. So there's lots of corner cases, lots of asymmetries in this protocol. It's not that everybody is doing the same operation in the same round at the same time, and then we go on to the next round. That would be actually much easier for formal methods. This kind of extremely asymmetric behavior means that it really exercises the edges of what tools could do. And in fact, we found no tool that could actually verify this protocol in 2018. So we had to build a whole new framework. So we built a framework called DY star. And the idea there was we will always have protocols like MLS, like maybe new protocols which use fancy new constructions, which will be beyond what crypto-focused tools like Proverif and Cryptographic can do. So in these cases, you would like to use a general purpose proof assistant, in which case we choose F star, but you could choose Coq or Lean or whatever, and do your crypto proofs in the general purpose assistant, where you can bring to bear all the proof techniques that you know, and you can really use any proof technique that actually works. So that's what we did. And so we wrote a specification of MLS in F star, and we verified one component of it with dy star. We are in the process of verifying the other components. So the first thing of note here is that we wrote a specification of the entire protocol in a modular way by breaking the protocol down into 3 components: TreeSync, which does group management; TreeChem, which does key exchange; and TreeDem, which actually does the DEM part of it, which is application data exchange. And it was a bit of work, but we could kind of decompose this protocol in this way. It would have been nice if the protocol had been written in this way, but no, we had to do it after the fact. And then we wrote bit level precise specification, which is executable, which means our spec, you can run it, it passes the test vectors from the RFC, it interoperates with other MLS implementation. So we know that we're not hiding anything. The details in our spec are really all the details of the standard. And then we did a proof on that spec. And the proofs are compositional using type checking in F star, which means they also are semi-automated. They're not push button. You have to do the proof, you have to do induction, you have to write your invariants. There's a lot of work involved. But in doing so, we can uncover attacks. And we did uncover an attack, I'll talk about it in a second. And once we're done, we can prove both unconditional theorems, which do not depend on whether you're in the symbolic or computational model, like, for example, the Merkle tree type properties, and you can also prove properties like this is symbolically secure. So that's what we did. There's one attack we found in MLS, which was a signature confusion attack. In one corner of TreeSync, there was a signature. In another corner of TreeDem, there was a signature. In the RFC, these are pages apart, many, many pages apart. Both these signatures use the same signing key, and the format of the data they were signing was actually not disambiguated with a label, which means they could actually be confused for each other. So you could take a signature from TreeDem and put it into TreeSync or vice versa, and it would work, or it could work. Okay? So this is a kind of format confusion attack between 2 different signatures. And we only found it because our spec was bit level precise about the whole of MLS. If we had just treated everything as tuples and stuff, we would have completely missed this attack. And this is not the only instance of these kinds of attacks. If you go look at recent attacks on Threema or Matrix, or old attacks on TLS 1.2 and X509, or even the attack I showed you on PQXTH with the key swapping, a lot of attacks on real-world protocols rely on format confusions. And we don't find them until too late because they are so boring to look at. Nobody wants to look at encodings. All of you guys want to do proofs on these super nice tuples and high-level structures, and so do I. Who wants to look at these serialization, deserialization thing and worry about whether this is injective or ambiguous? It's extremely annoying, very tedious. So my student, Theo Field, he built a tool called Comparse, which basically does all this boring stuff for you. You can plug in all the formats in MLS, which are like, there's like 100 formats or something, or all the formats in TLS, or all the formats that could potentially use the same key, and it will automatically try to prove that there is actually no collision between different things that might use the same key. Okay, so you can still do your proofs ignoring the formats, and Comparse will take care of the format checks for you. So it's a domain-specific tool that solves a particular niche problem, but it's embedded within F star. It's usable from the dy star proofs, so it all links up in a nice way. So this is one strategy we found for doing things which are like, solve small problems in ways that actually matter, rather than trying to always solve the largest composite problem. Okay, so I talked about trees, I talked about formats. Let's talk about implementation, right? If trees and formats are hard, implementations must be really hard to verify, right? Actually, no. For cryptographic algorithms, I would say verification problem is almost solved or solvable with a little bit of effort, let's say. So if you go look in the literature for almost any crypto algorithm you care about, there will be some project somewhere that has verified some assembly code for it, some C code for it, some Rust code for it, using either F star or Coq or EasyCrypt or some SMT solver or something or the other. There's a vibrant set of projects that are actively showing you how to verify crypto code. To the extent that I would not accept an excuse from anyone in the crowd here who says, I have an implementation, I'm going to give it to you, you should use it, and it's not formally verified. I'm like, why is it not formally verified? Why aren't you using one of these guys' project to verify it? And the way these projects work, many of them, not all, is something like this. You start from the standard. So in this case, this is CHA-20 Poly 1305. It's an IETF standard. It has some pseudocode written in Python. It has some test vectors, and that's how it specifies the protocol. But that's not good enough to do proofs with. So you first have to write a formal spec. You can write a formal spec in F star on top. That's what Hackle Star uses. Or in EasyCrypt, that's what libjade and the Formosa project use. You can write it in Coq. That's what Fiat Crypto uses. But it will be basically some encoding, some machine-readable encoding of what was in the standard. And once you have that spec, yeah, you use your proof framework, whether it's Coq or F star or EasyCrypt, to prove that your C or assembly or Rust implementation meets that spec. And what does that mean? You're looking to see, is there a memory safety bug in this code? Is there a panic in this code? Is there a functional correctness flaw? Is there input-output behavior mismatching with the spec? And in some cases, you can ask questions about side channel vulnerability. Either very crude ones, like is there a remote timing attack, or very specific ones. Is there a speculative execution bug here? There are tools for that too. Different tools have different capabilities, but you can ask these kinds of questions. So the good news is that for almost any modern crypto algorithm you could care about, there already is a verified implementation, or it's probably somebody is writing one right now. And these ones don't sacrifice performance. These implementations are as fast as handwritten implementation. Okay. Plus, they come with mechanized proofs. You can download the proof, you can check it yourself. And for the most part, you don't have to look in the proofs. And I think you really don't want to look in the proofs. But you can read the specs, you can read the theorems and try to make sense of them. And this is not just academic code. This code, this verified code, is currently running in Firefox, in Chrome, in Amazon, and so on. So this is really becoming a thing which is done, which is like mainstream. In my group, we've been maintaining two crypto libraries, Hacklestar and libcrux, since 2017. It's been 7 years. This library has grown to have a full suite of algorithms. It does entire cipher suites, all the algorithms that you might want. And it's also been deployed in various projects. The code is in C and assembly and WebAssembly and Rust, and it's all formally verified. But the interesting thing there, one thing that we don't realize, is the same kind of static artifact issue, which is that this library keeps evolving. We keep adding new crypto primitives to it. We add new constructions when they get standardized. But more than that, every time we do these changes, we have to worry, well, are we breaking the proofs? So the proofs for this entire project are on CI, and they keep running nightly for every code change. But not just that, the tools might change. The verification tool might change. The SMT solver might change. So there might be many reasons why your proofs break, not just because you change something, but because something in the environment changed. And this is an essential aspect of doing these kinds of projects, which is that you really have to treat your proofs like software and put them on CI and really maintain them, because otherwise they will bit rot, and 2 years later, nobody will be able to run or check that proof. All right, so we did a whirlwind tour through all of that. So let's now find the last bit, which is, well, you can do proofs on top, you can do proofs here, you can do proofs there. Can we somehow link them together? That's the holy grail, right? The end-to-end dream. Can we actually put all of these proofs together and link them in some nice formal way so that we know that the same security guarantees go all the way from the specification to the code, to the assembly, to the machine and whatnot. And indeed, there are some approaches that do this. So if you go to the Kyber talk at Crypto, you'll see how they're actually using the EasyCrypt framework to link all the proofs, both for the implementation and for the security in the same framework. Other people are trying to do the same thing, but maybe in F star, using F star as the meta framework within which all the proofs are connected, or Coq as a meta proof framework in which all the proofs are connected. And this is, I think, a laudable goal in the end. If we can actually have an end-to-end theorem, that would be amazing. But a part of me is also feeling whether this is actually a wrong direction in terms of practical formal methods. Because surely there is not going to be one proof framework which is going to be amazing at all the various tasks we want to do. Already we know there are 3 kinds of artifacts. Surely there must be some specialization in what we want to use in these 3 kinds of frameworks. So there's, as part of my company, Crispin, what we're trying to do is to try to do something a bit more pragmatic and less what you might call foundational, which is that we don't want to prematurely force a choice or the tool or the specification on you. So you can start writing your specs in Rust if you want, or Python, we don't care. We will generate the specs from there. You don't have to choose whether you're going to use EasyCrypt or Coq or Proverif. We will translate to whatever tool seems most useful for that particular task. In order to make all of this work, we also believe that there's a significant amount of investment you need to do inside the verification tool engineering, because the tools that we're talking about, I try to make them sound nice, but they're kind of hard to use. Okay? And part of it is because there hasn't been enough tool engineering invested in them. And part of it is because the users haven't been coming in and saying, I want this to be improved, and getting involved in this. Because I think in the end, what people want is to have customized versions of these tools for each problem domain, which are driven by the people who actually want to use these tools, like the people in this room. So the tool that we bring building, the tool chain, is called Hacks. And one of the ideas behind Hacks is that you write your specs in Rust, you write your code in Rust, and Hacks is going to compile it through the Rust compiler and then spit out whether if you ask for proverif, it'll give you proverif, or Coq, or F-star. There are backends in progress for EasyCrypt, Lean, and so on. Whatever backend you want, something will come out there, and you can then try to prove things there. Using Hacks, the first project we did was to verify an implementation of MLChem. So this implementation is written in Rust. It's also optimized for AVX2 and Neon and so on, and we're trying to verify those parts of it right now, actually. And this code is compiled to F-star using Hacks. And in F-star, we can try to prove things like this Rust code will never panic. We can try to prove functional correctness, that it meets the spec. And we can prove secret independence. It never branches on secrets or uses a secret as an index into an array. And you won't, for example, divide a secret by some other value. And in exactly proving the secret independence is where we found in our code a particular division vulnerability, which then we found in other people's code, and that became the Kyber/V1 bug. So it was found during formal verification. And once you have verified your code, we also have tools to compile this Rust code to C, because there are still many legacy libraries that cannot really deal with Rust. So in fact, the C code compiled from this verified Rust code is what is being now ported, upstreamed into NSS. And we're also working with Google on seeing how this could be put into boring SSL. But that's the crypto code. We can also use Hacks to verify protocol code. So we have a TLS 1.3 implementation in Rust. And what you can do with Hacks is say, this module is the protocol code. Please send that to proverif and analyze it there. This code is message formatting code. Please send it to F-star and try to prove things with comparse with it. We can do those kinds of things because we are in this framework where we don't commit to a single tool for all the action, all the proofs that we want. Okay, so looking forward, what are the things I'm most excited by? Going forward, there's on the symbolic verification side, already you can see in the Tamarin tool, for example, more and more attacker models being modeled in this that can find new kinds of attacks. It's getting really, really precise and very exciting. New attacks are being discovered automatically using symbolic verification. Also, automated tools are now starting to do more and more things like induction, so that they're closing the gap between proof assistance and automated tools. On the machine check crypto proof side of things like Cryptoverif, EasyCrypt, and so on, the most exciting new developments are towards modeling the quantum adversaries, including the QROM. And many of these tools have started working in that direction. Almost all of them support passive quantum adversaries today, but they are moving towards supporting active quantum adversaries. One project that I'm particularly excited by is called Squirrel, which uses symbolic methods to produce crypto proofs. So it really is the best of both worlds. If you want to understand a little bit about how it works, read this. It's a very readable little note that came out this year on how Squirrel works. It's starting to get really good traction, and this is one of the more exciting verification projects coming up. On the code side of things, I foresee that in another 5 years, almost all crypto libraries will only accept new code if it's formally verified. This is already turning out to be the case for boring SSL, NSS, and many other companies, and Amazon as well. Many other companies are starting to get into this stage where new crypto code should be formally verified. And the interesting new challenges there are on doing side channel analysis and being able to prove that your code does not have certain categories of side channels. On the protocol side, we are still very far. We are nowhere near being able to verify things like lib signal, but we are getting there with sort of these pragmatic tools like Hacks. And finally, I'm quite excited about lightweight formal methods, which don't require big proofs. Things like hack spec that allow you to write specs in a formal way, in a machine checkable way, and check small things about them. Things like proof log that allow you to check whether your manually written proof is correct without giving you any super serious formal guarantees. So to conclude, many of us work on exciting new crypto schemes, protocols, and so on. But getting this into the real world requires much more than technical finesse. It requires a lot of social communication, right? we need to write precise, well-documented specifications. That really helps. We have to be able to explain what our proofs are doing to people who are not experts. And the designs keep evolving, so we have to be able to answer questions about our designs quickly. But if we are willing to do that, getting involved in standardization procedures or in implementations has the potential to give a major impact to the work that we do. And formal methods can help answer these kinds of questions and help you do these kinds of activities. We've talked about symbolic and computational proofs and software verification, and these kinds of systematic tool-based analysis can really help us. So I would really encourage you to kind of come to me and ask me what tool you should use, but just start with any tool, try it out. Because the more you try it out and the more you ask for it to be customized for your use cases, the more effective will it be. That's my call to arms, and I'm done.
Thank you very much, Karthik. Do we have any questions?
Hello. So you said that it's essential for specifications to be human readable and machine readable, and I certainly agree on that. But by specification, you seem to just focus on the specification of the programs, the instructions executed by the parties, while I would say that even the security definitions should be part of the specification and should be machine readable and human readable. That would be very, very useful. So what do you think about that? And are we going to get there anytime soon?
That's a very good point. Thank you. Yes, so the specs that I wrote on the slides were all really the program or algorithmic specs. And that is true because they're the easiest to kind of depict. But in fact, in tools like Cryptographic, EasyCrypt, even ProVerif and Tamarin, a lot of the effort of modeling your protocol is actually writing down the security assumptions. And the assumptions are also machine readable. They are printable in LaTeX. And they've gotten to a stage where we can indeed get to this. We can say that we can have machine readable specs of the assumptions, of the security goals, of the definitions of the threat model. So the ProVerif model that we have for PQXTH contains all of these things. So does the Cryptographic model. It's a complete description of all of the things that you just mentioned. And this is indeed very much part of the spec. For standardization, maybe not so much, because they don't care so much. They should, but they don't. For a certain kind of human, yes.
So
The question was whether they're human readable as well, or they're just machine readable. The thing is, of course, what happens is that the syntax for many of these tools, for many of these definitions like ProVerif, Cryptographic, EasyCrypt, over time has evolved to be most suitable for verification, not suitable necessarily for the user. So that is a problem. And it is one that people are aware of and are working on. But yes, on the whole, I would say that if you are able to read the kinds of definitions that are in LaTeX in a paper, you will be able to read the kinds of definitions that are in Cryptographic or EasyCrypt.
My question is, are these compilers themselves formally verified? Because I'm now passing my trust into this tool. So what is the goodness of the tool?
So there are various levels of compilers. So there is, so for example, in the paper that you'll see at Crypto 2024 on Kyber, they use Jasmine, and there's a compiler from the Jasmine language to the x64 assembly set. And this compiler is verified. It's formally verified in COP with the foundationally verified. So that compiler is verified, but the distance is not so much. It's like an assembly-like language to assembly. There's also a compiler which goes from C to, I think it's only for Intel assembly, called ComCert. Well, actually, it supports other things, but I don't exactly remember the status of the proofs, which is also fully formally verified all the way from C to assembly. Now, the thing is, of course, that if you're talking about Rust, there is nothing which is formally verified there. If you want some other instruction set, they may not have a formally verified compiler. So this is still considered a big problem. So there have been like big efforts to do some things, and there needs to be other big efforts to cover the rest of the instruction sets and the rest of the source language. But I agree, we shouldn't put all our trust into the compiler in this kind of case. In my world, and again, I'm being pragmatic here, what I like to say is that we write our code in Rust, we compile it using LLVM, like the rest of the system is being compiled with LLVM. So yes, we are putting a trust into this compiler, but this is the same trust that you're putting in all the code around ours. And we do careful inspection of the binaries. We do run tools on the binaries to make sure that it did not introduce something strange. But this is not a formal thing. We don't have a formal proof that the compiler is correct, and you shouldn't trust it, and because it often screws up. But there are things that you can do which are more practical than saying, I will only use the system if everything is formally verified, because I'm afraid in that case, you will not use anything.
Hi. So I myself are not a formal verification person. I'm like a cryptographer who likes to do cryptography, like snarks, FHEs, threshold signatures, so on. So all these primitives, they sort of have sort of a lot of mathematical content that I think a lot of the theorem provers for crypto nowadays doesn't have, maybe doesn't have the tooling yet to be able to express these. Do you think that is correct? And like, if you were to try to formally verify these more advanced primitives, where would you start?
Right. So there is this whole range of tools that I was talking about, some of which are very specialized and do some things fully automatically, amazingly well, like Proverif. But they would not be the right tool for doing advanced algebraic kind of things with mathematical objects. But Lean is also a formal method. You could code up things in Coq, in F-star, in Lean, maybe even EasyCrypt, the FHE, you can code that up, prove properties about in all of these tools, because they are essentially general purpose provers. You can prove mathematical things in there, and people are proving mathematical things in there. So definitely you can do that. The question is whether you can prove security properties. So there is mathematical properties, like is this functionally correct, for example, that you can definitely do today. Now, whether you can prove security properties about them depends. So there are some nice works in EasyCrypt on trying to prove security properties about some of these constructions, maybe not so much else in other tools, but that's because we have been focused too much, I would say, on secure channels, because that's where the bang for the buck has been, like PQXDH, TLS13, and so on. But if people like you were to say, I want to formalize this and prove things about it, I'm sure the tools will move in that direction and make it possible for you to do that.
All right, well, if there are no other questions, please join me in thanking Karthik again.